In this video, you're going to learn what each of the different components of the model are, and then a little bit about how to start using your sand tank groundwater model. So this, again, is obviously your sand tank groundwater model. It's situated on these stands, these wooden supports, and that's located on top or situated on top of this Rubbermaid container, which stores your supplies, but also serves as a reservoir to hold water as we're going through these activities. When you first begin using the model, we encourage people to have these outlets, these little elbow joints pointed up. These elbow joints control water flow out of the model. You'll notice that there's a long, about a 2-foot tube that you can have on either of these outlets. And in this situation, I'm going to put the tubing on this outlet on the back of the model, and then insert the other part of that tubing in the Rubbermaid container through one of those holes in the top of the casing. The top portion of this model where we see the sand material is what we call an unconfined aquifer. That just means that the water in this layer is open to the atmosphere, hence the name unconfined, as opposed to this layer down here in white, which is labeled the artesian aquifer. We could also call that a confined aquifer. And the reason it's confined is we have this layer of clay. So confining layers or aquatards generally separate the unconfined aquifer from maybe a confined aquifer below it. We have different types of material in here. We have a coarse wedge of white gravel. We have some gravel down here. And the different types of material are important because they're going to allow us to do different activities that demonstrate how water moves through different types of material underneath our feet or in the groundwater, in the different groundwater aquifers. Other things to point out in this model are the different tubes. Some of the tubes are labeled piezometers. Those are these long, thin, narrow tubes here, here, and here. There's other tubes that are labeled pumping wells. And the pumping wells have a little bit additional reinforcement that allows us to pull a vacuum on those to simulate the impacts of, let's say, a municipal well or maybe a private well. But that reinforcement allows us to pump those with a little bit more vacuum so as not to damage the material or the membrane on the bottom of those tubes. When we look at the piezometers, one thing that I want you to understand is that these tubes, it's only the bottom of that tube that's open to the aquifer. And that's really important because this tube right here is only open to that lower confined aquifer, that artesian aquifer. And the point at which that tube is open allows us to measure the energy level of the water where that tube is open to the aquifer. So in the case of these artesian aquifer piezometers, these two piezometers are measuring the water level down here in this aquifer. These piezometers are measuring the water level or the energy level at different points within the unconfined aquifer. And I want to show you a unfilled model. So if we look, this is it's the same model, it's just unfilled. And if we flip it over, what you'll see is those tubes and how it's just the bottom of those tubes, or it's just the bottom of that well that's open to the aquifer. So again, these piezometers, because they're only open at the lowermost point of that tube, are allowing us to measure the energy level at the point in the aquifer which it finishes or which it's open to the aquifer. And this section is going to give you most of the tools you need to get you through the other activities. We're going to show you how to add water to the model, how to add dye to the piezometers, how to simulate pumping wells, how to add contamination to your leaky landfill, how to draw in the water table. Those are all the skills that we'd like to demonstrate in this portion of the video here. So for getting started, the main thing that we're going to want to do is begin adding water to our model. The groundwater is not going to be able to flow if we're not adding water through some sort of precipitation event or recharge event. And that's what these bottles are meant to represent. Again, are going to be rainfall or snowmelt, some of which is going to infiltrate through the soil into or eventually reaching a point within this model where all the empty spaces in the soil or all the cracks in the rock are filled with water. And that's again our groundwater, and that's what the sand tank model is going to allow us to demonstrate, is how that groundwater, one, gets into the ground, but once it's in the ground, how is that water moving? So these bottles are going to be rain or snowmelt, and to get your students excited, you might want to have them simulate kind of a thunderstorm or a rain event, or maybe make thunder or rain noises to help simulate the thunderstorm that's going to bring the recharge to our groundwater model. And it's really important to maybe show or demonstrate to students that recharge happens anywhere on the landscape where water can soak down into the ground. So using this bottle and pouring a little bit of water on that gravel layer will help them see that when that water hits the top of the model, some of that's soaking down into the ground. The other way we're going to add water is by flipping these bottles over into the little reservoir. Now this reservoir, you'll notice on the side, there's little slots that are open to that sand and gravel portion. So we're adding water to this little reservoir, but water in that reservoir is entering our model through the little openings in the side here. And here, we're gonna flip these bottles over. So you'll see I did that pretty quickly. As long as those rubber stoppers are on securely, we can flip those over, and now we're adding groundwater. We're adding rainfall and precipitation to our watershed or to our landscape. So as we do that, you might notice the water level in that river or stream starting to rise. And that's an indication that all the empty spaces in the soil or the sand are completely filled with water. So I mentioned that as the empty spaces fill, you're going to start to see the water level in that river, that low spot, start to rise. And that water rising is an indication of where the water table is at in the other portions of the model. The other thing you're going to notice, if the artesian well is not capped, you might notice some water coming out of the artesian well. And that's just because the artesian well is basically open to this confined aquifer down here. And because there's pressure of all the water, the water level here is exerting pressure on the water down here, which then pushes water up out of that artesian well. For the purposes of our demonstration, we want to basically plug our artesian well. So I'm gonna cap our artesian well as we get started here. Once the water level reaches the top of the lake or the river, you're gonna start to notice that the water flow from these bottles stops. Water only comes out of these bottles if it's got somewhere to go. So because basically all the empty spaces in the soil are filled with water, and the top of our water on both sides is at the top of these outlets, now there's nowhere for the water to go. So we're at what we would call equilibrium, and now is the point where we want to add some dye to our model. So you should have been given two different colored dyes, one red, one green, and the dye is just basically regular food coloring. If you run out of dye, you can make your own, but you do want to dilute it to make sure that we're not adding really concentrated dye to this model. The more concentrated the dye, the harder it's going to be to clean out. So the proper ratio of dye that I generally use is about 1 milliliter of food coloring to 100 or 125 milliliters of water. These are 125 ml bottles. So 1 milliliter of food coloring fill the rest of the bottle up with water. You should be at about the right dilution. If it's too concentrated, add a little bit more water. If it's too dilute, add a few more drops of dye. You'll notice that the dye is in bottles which only the small syringe is able to fit into. So just to make sure that we're not adding too much dye to the model, we've got it situated that only the small syringe is the one that you should be using to add dye to the piezometers. So for the purposes of this activity, we're going to start by adding green dye to all of the piezometers in the unconfined aquifer. And the unconfined aquifer piezometers are going to be this one here, 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 and here. So we're going to use the green dye. And here I'm going to demonstrate using our syringe. We're going to pull maybe 1 milliliter or 2 milliliters of dye out of this bottle. And then we're going to add dye to our first piezometer. Again, this piezometer here, we're going to want to add green dye to all the piezometers in the unconfined aquifer. So we're going to start with this one here. It's really important. Your syringe should fit into the piezometer in a way that allows you a pretty good seal. You might have to play around with it a little bit, push it in a little bit to make sure you got a good seal. You never want to inject the dye directly into the piezometer without removing a little bit of the air first. So you're going to see there's a little bit of an air pocket between the top of the piezometer and the top of the water level in the piezometer. So to avoid injecting air into our aquifer, you're just going to pull up. Once that air pocket's been removed, then you're going to push down, and you should see a little plume of dye come out the bottom. We're going to repeat that. So again, if you don't have enough dye, you might want to reload, so to speak. And we're going to do the same thing, where we're going to put our syringe on top of the piezometer. We're going to pull that air out, and then we're going to push that dye in. And again, you're going to push enough dye so that you have about a quarter size circle of dye that comes out the bottom of the piezometer into the aquifer. That's about the right amount of dye that you want injected into the model. I'm going to reload again. And again, we're adding green dye to all of the wells or piezometers in the unconfined aquifer. Here I'm going to demonstrate, I'm just going to push in. So we talked about what happens. We don't want to inject air. If we do inject air, it's not the end of the world. It just means that the model is not going to behave maybe how we want it to. Here's what it looks like if I were to accidentally inject some air into that piezometer. So we can see here, there's a little bit of an air pocket. And up here, we can see that the dye or that water level in that piezometer is higher than even the sand and the gravel. And that tells us that something's wrong. It shouldn't be behaving like that. This is what we should see. Here's the 2 piezometers that we were able to suck the air out and then inject the dye. You'll see that there's no air pockets. We have a nice quarter size circle of dye that came out the bottom. And then we look here, and again, here's our little air pocket. That's easy enough to fix, and we're gonna fix that right now. So to fix that air pocket, we're just gonna take our syringe, and we're just gonna basically suck that air pocket out. And if we suck that dye out, we just wanna inject that back in. So again, not the end of the world. If we do accidentally inject air, it's easily rectified by basically redoing that process. Pulling up until you get that air pocket out, and then injecting the dye back in a way that avoids that air pocket from being trapped in the model. And if we look at the top of the green dye in that piezometer now, we see that it's in line with basically our other piezometers. So we're going to continue adding green dye to these piezometers, and you might need to remove the bottle on the side in order to access these two last piezometers here. So again, we're going to suck air out. Once all the air is out, then we inject that dye. And one more time on the end. And here, because it's the longest piezometer, I want to make sure that I have enough dye and that I have enough room in my syringe to be able to suck that air out. There we go. Now we have green dye in each of our unconfined piezometers. Next thing we're going to do is we're going to add red dye to the piezometers in the confined aquifer. So here's our red dye. I'm going to do the same thing. We're going to find our piezometer in the confined aquifer. We're going to suck that little bit of air out. And then we're going to inject that red dye down into our confined or artesian aquifer. I'm going to reload. These are long piezometers, so they do take quite a bit of dye. I'm going to find the well in the confined aquifer. I'm going to suck the air out, and then I'm going to inject my dye. Any remaining or leftover dye you can put back into your bottle. So now at this point we have dye in all of our piezometers. We have green in the piezometers in the unconfined aquifer, and we have red in the two piezometers in our confined aquifer. Let's not forget to put, if we removed our recharge from this side, let's not forget to put that back. And you might be looking at it and saying, well, there's nothing happening. The reason we are adding dye is it's one, going to help us understand where the groundwater is moving within this model. And two, it's going to allow us to understand or measure the energy level of the water at the piezometer locations. Nothing's happening right now because the energy level in this model is equal, it's static. Here's our water level. You'll notice it's uniform across the top of this model. How we're going to change that is we're going to open the outlet on the back of this model. And with this outlet open, again, this low spot is going to be simulating a river or a stream. So it's like breaching the dam. As we rotate that elbow joint, we're going to release the water from our dam. Now this becomes kind of a cross section of a free-flowing river where we have the water coming in through our rainfall, and we have the groundwater flowing to our river or stream, and it's exiting out our river or stream on the back of the model here. And now with this outlet open, we should see the dye begin to move. At least some of the dye will begin to move, and some of it's going to move quicker or faster than others. And while we're waiting for that dye to start moving, again, because groundwater doesn't move with rapid speed, right? Groundwater moves relatively slowly through the tiny spaces in between the soil or the rock. Is what it's moving through. And while we're waiting for that to move, we're going to draw in our water table. So to draw on our water table, what we're looking for is the top of the water level in our piezometers in the unconfined aquifer. Again, the green piezometers are the ones that we're looking at. How do we draw on that water table? Well, we're gonna connect the dots. We're gonna look at the water level here. We're gonna find the water level here, 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 and here. And then on the other side, we're looking at the water level here, here, and here. So this is just a close-up of what the top of the water level, how we use these piezometers to measure the top of the water level. So if we want to know where the top of the water level is at, the dye in these piezometers kind of tells us that. The top of the water level in the piezometer, measured by that green dye, is the top of our water table. And here, if we connect these dots, let's use a dashed line to connect these dots, this then shows us that water table. Everything below that dashed line, all the empty spaces in the soil or all the cracks in the rock are completely filled with water. And everything below the water table is what we refer to as groundwater. Let's do the same thing on this side. If we connect these dots, there we have our water table. We can actually write that in if we wanted to. We could say water table, so that everybody viewing this demonstration knows that that's our water table there. The other thing we can see is that green dye is starting to move. And wherever that green dye is moving to is showing us the direction of groundwater flow. And where is it all ending up? It's all ending up in that river, that stream, right? So if we follow that green dye, we can start to see those groundwater flow paths. The last thing I want to do is help you understand how to use the pumping wells. So again, the pumping wells are this well here and this well here. This large 30 milliliter syringe is designed to be used with those pumping wells. And they work very similar to the piezometers in that you can use the syringe to pull water out. They're just reinforced because they allow a little bit more suction. And the more suction you apply, the faster the model will respond to that suction. So I'm gonna use this syringe to pump this unconfined aquifer. As we pump that unconfined aquifer, you can watch what effect that pumping has on the water level in the surrounding piezometers. And that's part of the activity that you're going to be doing, is pumping these wells in an effort to understand what influence pumping the different wells has on the water levels or the energy level in the different parts of the aquifer. But that's one way to pump the well, is by using the large syringe. The other way to pump that well is by creating a siphon to simulate kind of a high capacity well. When you pump using the syringe, you're going to notice that when you pump, you see the water levels changing. But once you stop pumping, the water levels return back to a normal state relatively quickly. A high capacity well is going to allow you to simulate kind of a continual pumping effect, which is going to be much more similar to what happens under, let's say, a municipal well pumping situation, or maybe an irrigation well pumping situation. And to simulate that high capacity well, we're going to use this long, narrow tubing. You can use one of the large blue syringe tips. And if you install that tubing into the blue syringe tip, and you use some of your Teflon tape, so you're going to want to use some of your Teflon tape to wrap around that blue syringe tip. And that's going to allow you to make a good seal with the pumping well. Without that Teflon tape, you might not have a good enough seal to start your siphon. But when you have your blue syringe with your tubing and the Teflon tape, you're going to insert that blue syringe into the pumping well, and then you can use your syringe, either one of them will work, to simply pump a little bit of water out. So as you pump, you should see some of that green dye enter the tubing. And then when you release the tubing from your syringe, you're going to want to make sure that you're near the outlet or the opening for your bucket. And if you insert that tubing into the hole of your Rubbermaid container, the water from that well or from that tube should flow on its own power. That's the siphon effect that's allowing us to simulate that high capacity well. Now with that well pumping, you're going to notice that the water levels in our piezometers have now changed. So we can redraw our water table to see what impact that high capacity well is having on our groundwater. So if we redraw, we see here the water table is quite a bit different. The water levels or the energy level in our piezometers is showing us the location of the new water table under these pumping influences. And we have this nice cone of depression that is formed because of the effects of that high capacity well. If we stop pumping, we can simply remove the blue syringe from our pumping well. The pumping stops and the water levels should start to return back to normal, unpumping influenced levels. So at this point, you have all kind of the tools you need to start exploring the model on your own. And we want you to use the activity sheets that we provided to follow these instructions and guide you through a series of activities to explore some of the different concepts that we'd like you to be able to understand yourself, but also be able to demonstrate with your students. So using the skills that we've kind of demonstrated in the last couple of minutes, we want you to start walking through this activity step by step. It should take maybe a half hour, 45 minutes. And we'll check in with you periodically to make sure that you're on track. If you have any questions as you go through this, feel free to check in with us, raise your hand. We'll come around to the different breakout sessions to check in with each group to make sure that you're on the right track. Once you're done going through these activities, we'll reconvene as a group to show you kind of additional care and cleanup instructions for your groundwater